welcome all of you. In the last class, we started discussing about relaxation time. Of course, before that we discussed something about various other things like pulse phase, receiver phase, and of course gradients, everything. Afterwards, I jumped into relaxation. I explained to you what is the relaxation phenomenon. For example, you take the sample outside and put it in a magnetic field. You know that in the absence of a magnetic field, the spins are randomly oriented. There is no preferential alignment of the spins. As soon as you put the sample in a magnetic field, immediately after the sample is put, we have what is called a saturation state. That is a state wherein both these energy levels for spin off system are completely occupied. In the sense, they are equally occupied. There is no population difference, that is what it means. That means that situation is called a saturation condition. So, immediately after you put this sample, you have a saturation condition. But give some time, then spins will develop some polarization. In the sense, it so happens more spins gets aligned along the direction of the magnetic field than opposing it. Of course, then we brought in the probabilities of spins going from alpha to beta and beta to alpha, and we worked out mathematically, and we showed that if that is the situation mathematically, this cannot happen. If I take n alpha and n beta are the number of spins in alpha and beta states, we did mathematical calculations and showed that somehow this was not agreeing with our assumption, because there is always some magnetization developed where the spins are preferentially aligned along the direction of the magnetic field. More spins are in the direction of the magnetic field than opposing it. So, there is some magnetization. So, we understood this by taking into account not the spin population of n alpha and n beta states, but deviation from equilibrium. Then we arrived at the expression. Then the expression what we got is how after certain time the magnetization grows along z axis. It requires a time, that time constant is called T1. This is what we arrived at, this exponential function. This exponential function is the one which is given as mzt is equal to m naught into 1 minus of exponential minus t by t1, and t1 is actually this one. This is time constant called spin lattice relaxation time. It is the time that is required for the growth of magnetization along the z axis. Okay. This is also called spin lattice relaxation or longitudinal relaxation also. There are certain synonyms for it. So, what is the meaning of T1? We understood it is a relaxation process by which the net magnetization returns to its initial maximum value, growth along z axis. This can happen as soon as you put the sample in a magnetic field, or you disturb this thermal equilibrium magnetization by applying a radio frequency pulse, and then it has to come back to equilibrium position, equilibrium condition. That means it has to attain its original value called m0, which is parallel to b naught, and this growth along z axis is what is called time, which is required for that is called spin lattice relaxation time, and this phenomena is called relaxation in the along the z axis, that is called spin lattice relaxation. In diagrammatically, pictorially in the vector diagram I showed like this. Immediately after the 90-degree pulse, the magnetization is brought to x or y axis by a 90-degree pulse. Immediately then there is a statistical phase coherence, all the spin vectors are aligned along this axis. But with time what happens is the spin start defacing in the xy plane, that I will come to that later, that is called another type of relaxation, and then simultaneously it starts growing along z axis. This decreases in the xy plane, start growing along the z axis. It so happens after a certain amount of time, which is called T1, the magnetization in the xy plane will be completely defaced, and there is a complete growth of magnetization along z axis, which is called T1. This happens as a function of time. This is what we understood. Okay. And there are certain synonyms for this, I told you. It is called T1 relaxation, longitudinal relaxation, also called thermal relaxation, and spin lattice relaxation. These are the synonyms which you find them being used in various textbooks on NMR. I just wanted to give you some of the synonyms. Please remember these things. Now, when the longitudinal magnetization M grows towards M naught, what will happen? The energy of the system will decrease, because as you know, once you give the somehow when there is a preferential element along mz, the energy of the system has to decrease. It can happen even when you apply a radio frequency pulse also. Apply a radio frequency pulse, you are disturbing the spin system, giving energy by external RF. Now the energy as a system must decrease. The reason is why it has to lose energy is because statistically there are more spins favoring the lower energy orientation, that is spin up or parallel orientation or in the direction of the magnetic field which is along z axis. Okay. So, this is the reason statistically, not that all spins will align, statistically more spins are favoring the orientation along the z axis. It is a parallel orientation. Okay. That is the reason why its system has to lose energy, energy must decrease for mz to grow along z axis. But one thing I wanted to caution you here, note these spins do not actually reside in the pure up states. I am telling you, it is only a statistical average. It is only the expected value of their aggregate angular momentum lie increasingly in the direction of z axis or in the direction of the magnetic field. Not that all spins suddenly align along the direction of the magnetic field. Statistically it so happens there is preferentially more spins actually will try to orient along the direction of the magnetic field. This is a caution, do not ever be under the impression spins of aligned means all are along z axis. No, there is also orientation along in the direction opposite to magnetic field. There is a preferentially excess magnetization, excess spins are in the direction of the magnetic field. This we have been discussing even from this first lecture itself in this course and also in the previous course. Now, when I say during this T1 relaxation system must lose the energy, it has to leave the energy from the same spin system, it will go out of the spin system, and when it leaves it is irrecoverable loss. It transfers to the system, where it goes we will discuss. The energy loss is irrecoverable and it represents transfer of heat. It gives to the surroundings in the form of heat. That is the way the system loses energy to the system, and that is the reason why in some books you say T1 phenomenon is also called attaining thermal equilibrium. That means system is attaining thermal equilibrium means because it had more energy, it will leave energy to the surroundings. After losing the energy it will come back to z axis. This loss of energy is not recoverable, it is irrecoverable loss of energy, and the way it will loses the energy is in the form of heat. That is why it is called attaining thermal equilibrium. These are the terminologies which we very often use in NMR. You must remember why it is called thermal equilibrium is because of this. Okay. Now you may ask me the question, okay, system is losing energy, fine, I understand, but where does this energy get transferred? Where does it go? What is the, who is that, where is the system which absorbs this energy which is lost by the spin system? This energy, it has to be transferred somewhere, and it gives its energy to other system called, it could be nearby nuclei, it could be nearby atoms, and also molecules through collisions, rotations or electromagnetic interactions. Varieties of interactions can be there. Somehow it gives energy to surroundings. In general you can call it as gives its energy to surroundings. That is why that is how the system gives, in the form of giving the heat to the system in the form of collision of molecule, rotation, giving some sort of a motion for it or some electromagnetic interaction. Or in other words, simply understand T1 is the relaxation, it is simply an energy flow between the spins and the external environment other than the spins of your interest. In the molecule, Let us say you are concentrating on the protons. The proton spins, we are worried about relaxation of proton spins. Apart from the spins of your interest, that is protons, everything surrounding it, which is called an external environment, we call by a collective word called lattice. It gives its energy to lattice. Please do not get confused with the crystal lattice, that is different. It is a rigid system, we can talk about crystal lattice. But here it is a colloquial word which is used as a lattice, in the sense everything surrounding the nuclear spin of your interest, entire surrounding system for which the spins are going to lose the energy or give the energy to them is called lattice. That is why it is called spin lattice relaxation. Spins are giving its energy to the lattice and then relaxing. That is why it is called spin lattice relaxation. Please remember this. Okay. Now, how does this exchange phenomena takes place? See, there must, when the exchange takes place, there must be some sort of a resonance. Let us have energy. How does the energy exchange phenomena mechanism is there? We will understand. Let us consider the spin system and also consider the lattice. The spin system has energy state alpha and beta. We know that we are considering the spin half nuclei. It has two energy states alpha and beta. I know what is energy separation. I can express in terms of frequency, that also you know. Okay. Now, the system has to give energy to the lattice from a perturbed state, from a disturbed state. That means the energy is already in the beta state. Somehow energy is already in the beta state. It has to give its energy to the lattice and come down to alpha state. It is a stable state. It has to come from disturbed state to stable state. That is, from beta state the spins have to come to alpha state. Okay. If that has to happen, you has to give the energy to the lattice. You should have the lattice system with identical energy separation. It is not spin system, it is the lattice now. You can think of lattice as different energy levels, which can be called as alpha and beta. Again, I mean, it is a colloquially, not spin alpha, spin states alpha and beta. I will call it lattice energy level as alpha and beta, so that this energy separation between alpha and beta of the spin system must exactly match with the energy separation for the spin system or for the lattice system. This lattice energy separation delta E must be equal to this thing. For example, delta E of lattice should be equal to delta E of the spin system. It has to match. Only then what will happen? The spins in the excited state, when it matches, gives energy to the lattice and comes down. When it comes down, what will happen? The lattice spins, lattice will absorb energy and these spins will go up. Okay? It goes to the excited state. See, when the spins are coming down here, it is lattice is going up, it is gaining energy. Here the spins are losing energy here. When the spins are losing energy, lattice is gaining energy here. See, it is gaining energy while the spins are losing energy. Only if this can happen, only if the energy states between spin system and the lattice agree with each other, matches. There must be equal, these two energy separation must be equal. And then energy, we call it as the conservation of energy, energy is conserved. The conservation of energy is satisfied, then there is a simultaneous transitions of spin from the nucleus upper state and the reservoir in the lower state. What happens? I mean, you go back here, there is a simultaneous transition of the spin from the upper state and spins in the lattice reservoir state. Okay. So, this is what happens. The reservoir lower state will gain energy and go to the upper state, spins in the upper state, lose energy and come to the ground state. This is what happens. Then nucleus will give up with energy to the lattice. You understand what I am trying to say? From the energy the separation between spins and the lattice, the spins in the excited state or in the upper state come down, simultaneously it gives the lattice absorbs energy and go to the excited state. That is what happens. Now you may ask me a question, why not spins and lattice both are in the upper states? Simultaneously transition cannot occur. Why not this will come here and this will also come here? No, it will not conserve the energy. That transition cannot occur. For that transition to occur, energy conservation will not be satisfied. So, as a consequence, only spins from the upper energy state will come to ground state, lower energy state. Simultaneously, the lattice will gain energy and go from lower energy state to higher energy state. This has to happen for the conservation of energy. Please remember, if both spins and lattice are in the upper state, there is no conservation of energy, and that type of transition simultaneously cannot happen. Okay. Now, okay, energy is transferred, I agree. How much energy is transferred to this lattice? It is a huge amount of energy. For example, the energy required, energy transferred to the nuclei is so small compared to molecular kinetic energy. There is always a kinetic energy system where molecular motions are going on naturally, thermal agitation is there. It is much smaller than that. The energy transfer from the nuclei to the lattice is much smaller than the kinetic energy of the system. So, and it quickly gets dispersed and largely goes unnoticed at the body temperatures. At the room temperatures, it largely goes unnoticed at all. That means, imagine a situation, you are like telling there is a big reservoir, big river, huge river is there, and it is at some temperature, reservoir water is at some temperature. Now, I am going to take a hot bucket of water. A bucket of water is very hot. I will transfer, I will pour that hot water into the river. River is so huge, and this will not raise the temperature of the reservoir, that is river. It cannot raise it. This one bucket of hot water cannot increase the temperature of the entire river. Exactly similar to that, this energy quickly get dispersed among the lattice, among the surroundings, and it largely gets unnoticed at all. That is what happens. It is a very small energy compared to kinetic energy of this system. Okay. Now, we can see the requirements for the relaxation. Okay, we understood spins will relax and give the energy to the lattice. The amount of energy also is we know it is very small, it quickly dispersed, and the way it gives energy is in the form of a heat, and we also understood it is a small amount of heat compared to the kinetic thermal kinetic energy of the system. I understand. Now, when can such a situation occur? How can the spins relax? What is the way it has to transfer the heat? There are certain requirements for it. It cannot just like that spin cannot transfer the energy to the lattice. And one of the thing for a spin system to successfully relax, it is a need of, we require the spins to relax. If the spins do not relax, you cannot do another experiment. The spins has to relax, go back to z axis, so that again you can pulse and you can collect the signal. This is a repetitive phenomenon, you can keep on doing the experiment. So, spins has to go back, has to relax and attain thermal equilibrium. For such a successful relaxation mechanism, there are certain requirements. One or two conditions I tell you. There must be an interaction which works directly on the spin system. The interaction must work on the spins. That is the type of interaction. And secondly, interaction must be time dependent. It cannot be static. If the interactions are not time dependent, what will happen? It will only vectorially add to the magnetic field. The interaction should be in such a way, it should perturb the spin system. Let us say magnetic field is along this axis. If it is a static magnetic field, it will simply add to the magnetic field, or if it is in the opposite direction, it will subtract to the magnetic field. It will vectorially add to the main magnetic field. It does not help you. For spins to relax, the main condition is the interactions must be time dependent. Okay? And not only that, it should work directly on the spin system. These are the two important conditions for a successful relaxation mechanism. And what is this time dependence interaction? What is the interaction time? It is see, you can talk in terms of microsecond, millisecond, like that. It should be the NMR time scale. Remember, NMR time scale is microsecond. Okay, so it should be of that order. The interaction between the spins and the surroundings must be of the order of microsecond at the NMR time scale. If the interaction takes for, let us say, for seconds or femtosecond, much shorter than that or much larger than that, it will not perturb the spin system. It must be in the NMR time scale. The interaction has to be in the NMR time scale. Okay. The implication now, these, what do you understand from that? You consider there are various motions present in the molecule. There could be electronic motion, there could be vibration motion, all those things. Okay. In addition to thermal motion like agitation, like random fluctuations, everything would be there. But important thing is you should know electronic motion and molecular vibrations do not affect NMR relaxation. They have a very little effect on NMR relaxation. These things contribute negligible or almost nothing it contributes as far as the relaxation of the nuclear spins are concerned. For NMR relaxation, electronic motions and molecular vibrations have little effect. Then what is that which is required? What are the thermal motions that are required? The frequencies should be of the order, thermal motion should be of the order of Larmor frequency. The Larmor frequency is the frequency at which the spins resonate. The interaction frequency, the energy of interaction should be of that order. It should be thermal motion frequency should be, it should cover the broad range of frequencies, so that it will give rise to, it will contribute to NMR spins relaxation. It should cover broad range, not a one monochromatic frequency, at a single frequency. It should have a wide range of frequency. If you consider such wide range of frequencies, several thermal motions you can think of in a liquid, where you can have not one frequency or a wide range of frequency, then it can induce relaxation. It can contribute to NMR spin relaxation. But of course, when I take the wide range of frequencies like this, so many frequencies are there in this broad frequency band. Not all of them will contribute. Only certain things which matches will contribute for NMR spin relaxation. The frequency of this should match for the energy separation of the nuclear spin, such that the interaction energy should aid the relaxation. That should be of that order. So, all frequencies in the broad range will not aid in the relaxation phenomenon. So, please remember, there are thermal motions are required in the liquids. There are thermal motions which cover broad range of frequencies. Only selected few frequencies aid in the NMR relaxation. So, now we will talk about the energy emission. How does the energy emission takes place and everything. The energy emission from the spin system to the lattice, of course, from the we already discussed with the energy level, spins in the upper energy state of this thing comes to the lower energy state. Simultaneously, lattice go from lower energy state to higher energy state. That is what we discussed. There is no doubt about it. But then how does the spins which are in the upper state will come to ground state? Who will induce the transition? Can there be a spontaneous emission of energy? Can the spins in the excited state spontaneously come down to the lower energy state? Spontaneous emission in the NMR frequency range is quite unlikely. In the radio frequency range, spontaneous emission is very unlikely, because it goes by the cube of frequency. So, it is not possible. So, any transition, any energy emission of the spin system between two energy states, from upper to a lower energy state, if the spins have to come down while emitting energy, it must be stimulated. It must be stimulated through other fluctuating magnetic field. So, the stimulation comes by another fluctuating magnetic field. Please remember that all the energy emissions in NMR must be stimulated. Spontaneous emission of energy is very unlikely, and this stimulation comes by other fluctuating magnetic field. So, the fluctuating magnetic field must be generated. When these fluctuating magnetic fields are generated, that will stimulate emission of energy. Please understand the concepts now. Slowly I am going step by step. We understood the energy emission is there, and the energy emission from spin system to lattice, but the reason for emission is not spontaneous, and it has to be stimulated. The simulated emission comes because of the fluctuating magnetic field at the site of the nucleus. That is another thing. Okay. The fluctuating RF field again must be at the Larmor frequency in the transverse plane, because spins are already in this transverse plane. If the spins have to give energy to the lattice and go back to z axis, and it must be in the Larmor frequency. Only then if the interaction fluctuating field RF field that is generated, if they are at the Larmor frequency in the transverse plane, then spins will emit, that will aid in emit when the spins or stimulate the spins to emit radiation. The fluctuating field that is generated in the transverse plane must be in the Larmor frequency range. This is an important point, one should remember this. Okay. Now you may ask me, okay, there is a fluctuating field that is there, that can aid in that is a source for stimulated emission. This fluctuating field that is generated in the transverse plane at the site of the nucleus. But how do this fluctuating field generate? That is the next question. You understand the concept. Spins require the fluctuating magnetic field at the Larmor frequency in the transverse plane for emission of the energy to interact with the spins, so that spins can lose energy and stimulate emission can take place and give its energy to the lattice. But the question is, what is the source of this fluctuating magnetic fields in the transverse plane? There must be some phenomena which generates these fluctuating fields. Okay? And these fluctuating fields originates because of motions of the molecules. These motions, I said, I told you this has least effect and it comes because of rotation, diffusion, molecular. This you can ignore. There are various types of motion, but mostly the rotation motion of the molecule, diffusion and some thermal agitation, random fluctuations, these are all responsible for that. Okay. Remember, the sources of the local magnetic field originate because of motions of the molecule, because of rotation, diffusion and random motions, all those things are responsible. And they must be time dependent. It cannot be all the time same rotational frequency or same diffusion frequency. Molecule could be continuously undergoing diffusion, okay, or continuously maybe at rotation, as it keeps on changing. It should be a time dependent field. That is important. If that happens, then the local fluctuating fields at the Larmor frequency responsible for stimulated emission of the energy takes place. You got the point now? The stimulated emission comes because of the fluctuating magnetic field generated in the transverse plane at the Larmor frequency. And the source of that fluctuating magnetic field are motions of the molecule, especially the rotational motion, molecular chaotic motions or diffusion or some random fluctuations. All these are necessary. There could be many. All are responsible for the spins to create local magnetic field, and all of them are time dependent. Very important. I told you already. If they are not time dependent, it will vectorially act to the main magnetic field. That does not help us. Okay. So now only the chaotic tumbling motion of the molecule is appropriate for spin relaxation. Varieties of motions are there, molecular motions, but please remember, chaotic tumbling motion of the molecule is appropriate for spin relaxation, nuclear spin relaxation, because that can generate fluctuating field at the Larmor frequency. The chaotic tumbling motion, random fluctuating motion of the molecule creates a fluctuating field that is appropriate for nuclear spin relaxation. Please remember that one. Okay. Various molecular motions are there, especially this chaotic tumbling motion is important. Other motions could be present like vibration or electronic transition, etc. They are either too fast or too slow and will not contribute for the relaxation. Get the point now? Fluctuating magnetic field, the source of fluctuating magnetic field understood, how it gets generated. Now a very interesting question will come. So far I was telling you we have generated a fluctuating magnetic field at the Larmor frequency. That must be B1 field, similar to your RF field which you apply externally to induce or to tilt the thermal magnetization, which is the thermal equilibrium, to XY plane. That is a B1 field. That is also at Larmor frequency. Remember I told you, see there is a alignment of the magnetic field in thermal equilibrium, magnetization in thermal equilibrium along the Z axis. It is a equilibrium, in equilibrium magnetization is perfectly aligned, there is no motion. Now what I am going to do is I will send a RF pulse in the direction perpendicular to it and I bring the magnetization to another axis. And this RF we are going to apply B1 field at the Larmor frequency. that we have been discussing in the very first class. But now also I tell you the fluctuating magnetic field that is generated in the transverse plane because of the random chaotic tumbling motion of the molecules is also B1, that is also at Larmor frequency. Now here two interesting situations we have got. External field we apply is also at B1 field is also at Larmor frequency, and the fluctuating magnetic field generated at B1 in the transverse plane B1, that is also at Larmor frequency. Then what is the difference? That is the next question. Both are at Larmor frequency, but the difference is one thing you should know: the B1 field, external B1 field I should say, not B1 field, externally applied RF field, which affects all the spins uniformly. It excites the spins in the sample continuously, uniformly it excites. For example, there are so many spins are there, so many transitions frequencies are present in the system. If you analyze the spectrum, there may be so many frequencies are present, but then all the spins are uniformly excited. It affects all the spins, and then you correct the FID and do the Fourier transformation. So the B1 field, RF field which you apply externally affect all the spins uniformly in the sample, whereas the fluctuating fields are local, random in magnitude, and affect only few spins. Very important thing. See, that is the important point. If there are several nuclear spins in a molecule, take a structure of a molecule, different protons are there in different chemical environment. But as we go ahead, we will see that different spins will have a different relaxation time T1. That is because you know that spins will relax differently, and then as a consequence for that to relax, the random fluctuating fields are also not same, they are different. So the at the magnetic field generated at the locally at the site of different spins are different. So it does not affect all the spins uniformly, it affects only a few spins. This is the main difference. The external RF affects all the spins uniformly, whereas the fluctuating magnetic field generated in the transverse plane also at Larmor frequency affects only a few spins. This is the main difference, this thing. So now the time is up, we will come back and understand much more about these things. So I am going to stop here, but please remember one thing what I was telling you today. We were discussing about the relaxation phenomenon, especially the spin lattice relaxation. I discussed with you and told you what is a lattice. This lattice is not like a crystal lattice, it is not a rigid system. In the liquid solution state, anything other than the spins of your observation is called a lattice. Anything surrounding the spin of your interest is called a lattice. And then the energy of the spins will give energy to the lattice. The way it gives energy is in the form of a heat, extremely small amount of energy, less than the kinetic energy, and quickly get dispersed at the body temperature. Its effect is less noticeable, not even noticeable. I told you, I gave you an example. In a big river or a big ocean, put one bucket of hot water, the ocean temperature will not rise. It may rise by 1/10 of a millidegree or microdegrees, very small. Effect is not going to be felt at all. Similarly, the energy which is going to be lost by the spin system to the lattice is largely goes unnoticed and quickly dispersed in the lattice system. That is what is going to happen. Okay. And then we also understood for the efficient relaxation phenomena we require a fluctuating magnetic field. It is a stimulated emission. The stimulated emission happens because of the fluctuating magnetic field. This is generated with the chaotic tumbling motion of the nuclear spins or system. Common like electronic or vibration transitions have least effect on spontaneous emission. Spontaneous emission is not possible here, only stimulated emission. So it has the least effect. So chaotic motion and this should be time dependent, which is at the Larmor frequency in the transverse plane, affect the spins. Okay, then only spins will lose energy. That is the stimulated. Actually, these are the things which causes the random fluctuating field, causes the spins to lose energy. And we saw the difference between the random fluctuating field and the external RF field, both at the Larmor frequency. But the external RF field will affect all the spins uniformly, where the fluctuating magnetic field in the transverse plane affect only few spins, and different spins will be affected with a different fluctuating fields. So, with this I will stop here, we will come back in the next class and then continue further, understand more about the concepts of this T1 relaxation and also T2 relaxation. Thank you.